Good evening, and thank you for joining us for this live-streamed presentation, Neutrinos, the Ghosts from Space, with Jonah Miller. I am Joyce Guzik with the Pajarito Environmental Education Center, also known as PEAK, located in Los Alamos, New Mexico, and I will be the moderator for today's talk. We are able to offer programming at this time because of our wonderful members and donors. So we'd like to thank you for your continued support. So now I'd like to introduce Jonah Miller. He received his PhD at the Perimeter Institute for Theoretical Physics, and this is near Toronto, Canada. He is now an astrophysicist at Los Alamos National Laboratory. His research focuses on using big computers to model black holes, neutron stars, and supernovae. So we're excited to hear about these ghosts from space. So I will turn it over now to Jonah Miller.
Hi, everyone. Nice to see you all here. So I'll hide my video for now so that you can better see the screen. But I'm still here. So our story begins, as most good stories do, with radioactivity. And you may recognize some of the people who, in this picture on the left, this is Henry Becquerel. And on the right, this is Marie Curie of Nobel Prize fame and her husband Pierre in their laboratory. And an experiment that these folks did back in the day is they took some stuff. At the time, they didn't know that these were atoms, really. And they noticed that some of this stuff would radiate energy. They didn't know what it was, but they noticed that, say, if you put this radioactive material in water, it would make the water hot. And so after a lot of experimentation, they found that if you took what we now know as a radioactive atom and you set it next to, say, a bunch of sheets of aluminum, then some of the material, some of what it emitted, some of this radiation, would go through a bunch of the aluminum sheets, and we now call that beta radiation or beta particles. And some of it would bounce off, say, a single aluminum sheet, and we now call that an alpha particle. And now we know that there's a third type of radiation or radioactivity, gamma particles, that goes through all the aluminum sheets. And I'll talk about that briefly a little bit more later in the talk. And so what's going on here? Well, you may recall that an atom is made up of protons and neutrons that live inside the atomic nucleus. Protons are positively charged. Neutrons are not charged at all. They're neutral. And then orbiting the protons and neutrons are electrons. Now, I say some terms and conditions apply because this isn't really what goes on inside an atom. It's a lot more complicated. There's the electrons don't really orbit. They're in quantum wave functions, et cetera, et cetera. There's a lot more going on. But for the purposes of what we're talking about tonight, this is a good picture. And what is this alpha radiation and this beta radiation? Well, we have to zoom in on the nucleus to figure this out. So it turns out that what alpha radiation is that your nucleus containing protons and neutrons spits out 2 protons and 2 neutrons all stuck together, which that's an alpha particle. It turns out that that is actually the nucleus of a helium atom. Beta decay, on the other hand, you have protons and neutrons in your nucleus, and it spits out an electron. Now, I told you that the nucleus contains protons and neutrons. The electron doesn't live in the nucleus. That's true. I'll explain what happens here in a bit, but for now, the important thing is that beta particles are electrons. And this has some interesting implications. So you may recall the periodic table of elements. And the number on above each element name is the atomic number. It's the charge of the nucleus. And so if you're spitting out protons and electrons, very interesting things happen to your elements, these things which are the building blocks of everything. So for example, if a uranium atom emits an alpha particle, it loses 2 protons. The charge of the nucleus goes down by 2. And so the uranium atom, its atomic number goes from 92 to 90. It becomes thorium. It becomes an isotope of thorium, technically, because the number of neutrons might not be correct, and it might be an ion because the number of electrons might not be correct, but nevertheless, it's thorium. Similarly, if say, if carbon undergoes beta decay and emits an electron, well, electrons carry negative charge. So the charge in the center of the nucleus loses one negative charge, i.e. it gains a charge. And so it goes from atomic number 6, if it's carbon, to atomic number 7. It becomes nitrogen. In other words, it's alchemy. Via this kind of process, you can convert iron into gold. This is not something you can usually do, but at some level it happens all the time in these kinds of systems. So let's go back to beta decay, where you emit this electron. What's really going on there? Well, it turns out that neutrons are not all they appear. Neutrons can be broken up into a proton, which is positively charged, and an electron, which is negatively charged. So the proton plus the electron, that's zero charge. That's why neutrons are neutral. And this other thing called a neutrino. So what happens when beta decay happens is you emit the electron, and so this neutron becomes a proton, and on top of that, this other thing that comes out is the electron antineutrino. And in a lot of ways, this is like chemistry. You may remember from school that there's exothermic and endothermic chemical reactions. Exothermic reactions produce heat. Endothermic reactions require heat to happen. Well, it turns out that one way that exothermic reactions can produce heat is via something called chemoluminescence, where the reactions actually require the emission of light or photons. That actually turns out what those gamma particles are. Gamma radiation, it turns out, is just the emission of light. But chemoluminescence is the process where in chemistry, the chemical reaction emits photons fundamentally as part of the chemical reaction. And these nuclear reactions, alpha decay, beta decay, they're very much like chemistry. They're nuclear chemistry, if you will. And instead of photons, the light that's emitted in those chemoluminescent reactions, it's neutrinos. Neutrinos are essentially the atomic nucleus equivalent of photons in nuclear chemistry, as opposed to the chemistry between atoms. Chemistry, normal chemistry we might think of is, two atoms come together and then that's something new. In nuclear reactions, it's two nucleons, particles inside an atomic nucleus. And it turns out neutrinos have three flavors. There's electron neutrinos, muon neutrinos, and tau neutrinos. And moreover, there's actually 6 kinds, because each of these has an antimatter friend. So there's electron antineutrinos, muon antineutrinos, and tau antineutrinos. And I showed you this picture before of the penetrating power of alpha particles, beta particles, and gamma particles. Well, neutrinos, they don't just go through the aluminum, they go through the Earth. They go through pretty much everything. And they're everywhere. These are 2 images. I really like these images. On the left is a bubble chamber from CERN. So what is a bubble chamber? It's basically just a space filled with gas. And when particles travel through it, like subatomic particles, they make traces in the gas. And you can see those lines through this chamber. That's the bubble chamber. Many of those spots and lines in this thing, those are neutrinos. And on the left, that really beautiful image is a similar bubble chamber experiment from Fermilab in Chicago. Neutrinos can be produced in the atmosphere. And the really cool thing about neutrinos is that because they go through everything, they're kind of like X-ray machines. X-rays are a form of light that go through our bodies but get stuck on our bones. And so if you use X-rays, you can see inside the human body. Well, neutrinos go through everything. So if there was some stuff that you wanted to see inside, then you could use neutrinos to see through whatever you're looking at and maybe get at what's going on really deep inside that thing. And that is in fact true. So one great example of this is our sun. So our sun, big ball of hot gas that it is, the light coming from it, for the most part, comes from what I'm going to call the surface. It's also called the photosphere. This is not really a surface. It's the point where the sun becomes transparent to light. But if you stood there, you would fall in and also burn up. The neutrinos, however, come from the very core of the sun, and they just go straight through all the gas between the core and the surface. And the core is where all the cool stuff happens. This is where the nuclear fusion that powers the sun is happening. And that's why neutrinos are produced there. Remember that neutrinos happen in chemical, in quotes, reactions between nucleons. That's nuclear fusion, nuclear fission. When atomic nuclei fuse or fizz, break apart, neutrinos are produced. And so we can learn about the nuclear reactions that are powering our sun by watching the emission of neutrinos from the sun. And so people tried to do this all the way back in the 60s. The first example of this was the Homestake experiment, which was a giant detector built deep underground in the Homestake mine in South Dakota. And the reason that it had to be in South Dakota, well, it doesn't have to be in South Dakota, but the reason it has to be in this deep mine, Homestake mine, is to prevent other subatomic particles from interfering. Neutrinos go through everything. They don't care about all the miles of rock between them and the experiment. They go straight through. But for example, other kinds of particles, such as muons produced in our atmosphere, they can't get to it. And so they get stopped by all the rock. And this protects the experiment from contamination. But there was a problem. When people tried to do this experiment, for example, there were more than just the Homestake experiment. They didn't see as many neutrinos as they expected. People worked out on pen and paper, given the nuclear reactions they thought were happening in the sun, what should the number of neutrinos that we see be? And this graph is showing, for example, that the Homestake experiment saw only a third, essentially, of the neutrinos they thought they should see. So what's going on there? Well, there was a big hunt to figure this out. Lots of different neutrino detectors were built, searching for the missing solar neutrinos. On the left, I'm showing Kamiokande in Japan. This thing is enormous, as you can see. When this thing is operational, that entire cave or cavern is filled with water, but they've sort of dropped it so that those scientists can work on it. On the right, that's the Sudbury Neutrino Observatory, which is in Sudbury, Ontario, deep underground in a copper mine. So the secret, and this won the Nobel Prize, is that neutrinos can change into each other. Each of those, the Sudbury experiment, for example, and the Homestake experiment, we're all only looking for one kind of neutrino. But it turns out that if you add up all the neutrinos, the total amount of neutrinos is correct. It's just that the types were not. And we now know that what's happening there is that electron neutrinos can transform into tau neutrinos or into mu neutrinos and vice versa. And so what's going on here is that the neutrinos were emitted from the sun as, say, electron neutrinos, but by the time they got to us, they had transformed into muon neutrinos or tau neutrinos. And this is called neutrino oscillations. So what's next as far as neutrino detectors? Well, now that we can detect neutrinos from our sun, we're looking a bit further away. And one way that we can do that is a detector like IceCube, which this is a picture of it at the South Pole. You can see the aurora borealis, well, aurora, not borealis, but the southern equivalent of that in this picture. But this image is actually just the tip of the metaphorical iceberg. IceCube actually is much bigger. So at the top is that facility you just saw, but the actual IceCube detector is a cubic kilometer of ice in Antarctica. You can see a picture of the Eiffel Tower here for scale. And wired out throughout this cubic kilometer of ice are all the little bits of the detector, individual scintillators that help us detect when a neutrino passes through this cube of ice. And IceCube is incredibly sensitive. It can detect neutrinos from way beyond our galaxy, as I'll talk about later in the talk. Which brings me now to neutrinos from space. So I told you that neutrinos are this great X-ray machine for stuff like our sun. Well, they're a great X-ray machine for a bunch of other stuff in space too. And so now I'm going to give you a little bit of a whirlwind tour of some of my favorite things that neutrinos are either important for in space or that are a key tool that we can use to understand them better. And I'm going to start with something related to our sun. What happens when a massive star dies? This star is much more massive than our sun, maybe 30 to 100 solar mass times the mass of our sun. And these very massive stars, over the course of their lives, they produce sort of an onion structure. So what happens is that the core of the sun is fusing elements. It's taking hydrogen atoms and fusing them together into helium. And helium fused more into heavier elements and heavier up till iron. And the reason that it's up to iron is that when you fuse elements, you get energy out from the fusion process up to iron. At that point, creating heavier elements than iron takes energy. And so the fusion process that's supporting the star stops, and the heat that was holding the star up goes away, and then the star will collapse. And so at the end of the star structure, you get an iron core surrounded by silicon, oxygen, all the way up to a helium envelope, or hydrogen envelope. The fusion stops, and the envelope falls in on the star, no longer held up by the power in the core. And when this happens, it compresses the core because it's basically collapsing under its own weight. It compresses it so much that the atoms in the core get mashed together into just one big atomic nucleus, essentially. And this thing, this now ultra dense thing is called a protoneutron star. And that is dense enough to support itself against the gravitational pull. And so what happens is once this protoneutron star forms, the stuff that's falling on it bounces off and moves away again. And this forms what's called a shock. And eventually, if you're lucky, if the star explodes, not all stars do, that shock will expand outward and move and eventually create a massive explosion called a core collapse supernova. And these kinds of explosions are quite visible. For example, this is a picture of, in 1987, there was a supernova in our own galaxy called SN 1987A. And on the left, I'm showing an image from the Schmidt telescope of a starscape. And you see that super, super bright star? That's not a star anymore. That's the death throes of one. That is the core collapse supernova explosion, outshining everything else in its vicinity. On the right, I'm showing what that same star, way zoomed in with a Hubble image, just 11 years ago, in 2010, many decades after the original explosion. And now what you're seeing is what's called the supernova remnant. This is the expanding cloud of gas left over after the explosion. That's what that ring is. There's nothing to stop it in space. So one thing that was puzzled scientists for many years about core collapse supernovae is that if you just do the math about the core collapse and then the shock, you find that, and if you do computer simulations, you find that the shock doesn't expand outward. It stalls, it fails, and then the explosion doesn't happen. It turns out that the key to powering the explosion is neutrinos. This super dense thing, this protoneutron star, is emitting neutrinos because it's forming one big atomic nucleus. Nuclear reactions are happening there. Nuclear chemistry is happening there. And neutrinos are emitted. And those neutrinos, most of them escape because they go through everything. But a few of them get absorbed behind the shock, and they heat the gas. And that heating, just a fraction of the neutrinos getting absorbed, the heating from those neutrinos is enough to expand the gas and power the explosion. And When we saw that galactic supernova in 1987A, we learned this for the first time because we detected neutrinos from that explosion in the star. It was a beautiful observational confirmation of the theory of core collapse supernovae at the time. The next thing I want to talk about is neutron star mergers. You may have recalled from 2017 where there was a big hullabaloo about the detection of the collision of two neutron stars, which produced something. The claim was that this produced like a Jupiter's mass worth of gold. And this is where all the heavy elements heavier than iron, are supposed to come from. That's all true. And I'll explain to you a little bit more detail how that works. And one reason astronomers liked this observation so much is because we got a lot of data. We observed this event in all sorts of ways: gravitational waves, gamma rays, X-rays, optical. There's something, I've heard statistics that essentially something like half of the astronomers on the planet were involved in this observation or in the subsequent analysis. So what is a neutron star? We talked a little bit about this. I mentioned this thing called a proto-neutron star, which happens after when the core of a dying star collapses, and we call this a core collapse supernovae. That thing is left over after the star explodes very often. And it is that iron core that's been scrunched up to such densities that it's basically one big atomic nucleus. And this is a really crazy thing. You get something that's as massive as our sun, because the original star was something like 30 times the mass of our sun. Its core is like the mass of our sun, but compressed to the diameter that it would fit inside Los Alamos County. And this is a picture of such an artist's depiction of a neutron star superposed on top of Manhattan Island. And these stars typically live and die in binaries. Most stars are born orbiting each other. So our system is actually kind of special. We only have one sun, but most solar systems have two suns orbiting each other. And eventually those suns undergo core collapse. Perhaps if they're massive enough, they explode, and you're left with two cores of dead stars, potentially two neutron stars. And over many, many years, the orbit of those two cores of dead stars, these two neutron stars, the orbit decays due to the emission of gravitational waves. And eventually, they collide, as shown in this video that I'm showing you on the left here. And they produce these spiral arms of gas coming off in the merger. And what you eventually get is some kind of remnant, potentially a black hole or a stable neutron star, or a hypermassive neutron star that eventually collapses into a black hole. And some of that gas, these spiral arms of stuff, some of it falls back into an accretion disk. Accretion disk meaning just a disk of stuff that's falling onto the orbiting and then slowly falling onto the remnant. And you get an expanding donut of stuff also from the stuff that escapes and doesn't form the disk. And so that's what I'm showing here on the right, is sort of a diagram. You get this, the red is this expanding donut of stuff produced by the spiral arms. The black is a black hole central remnant. And then there's a disk of stuff falling onto the black hole, accreting, that's the technical scientific word. And this disk of stuff produces a wind of material off the surface of the disk in this sort of spiral or peanut shape. And as you might guess, because the stuff is like, these original neutron stars were just made of atomic nucleus stuff, the disk and the donut are also made of nuclear stuff. And they're very heavy in neutrons. They're very neutron rich. And because there was just a massive collision, they're very hot. And this is the ideal place for one type of nuclear chemistry, the type that produces heavy elements, to occur. This is called R-process nucleosynthesis. And what I'm going to show you on this diagram is a little bit how that works. Not in too much detail, but a little bit. So what I'm showing you here on the x-axis, horizontally, is neutron number, and vertically is the number of protons, the number of protons. And what this is a periodic table of elements, much like the one you saw before, but a little screwy. So the line of dots down the diagonal, it's kind of the center of the plot. The solid ones, those are the elements we know and love. Everything else is an unstable isotope. It's an atom or an element that can only exist for a short amount of time. And so what you'll see is that if you have a lot of neutrons and it's very hot, then you can take whatever stuff you have and it will start to absorb all those neutrons and climb up the bottom of this periodic table until it runs out of neutrons. And then these elements are highly radioactive and they'll decay back to the line of stability, which is the periodic table we know and love. And so that's what you're seeing here in this movie. And these elements that are produced when this radioactive decay happens, it produces a lot more heat and a lot more energy. This radioactive decay glows very brightly. And the color of the glow depends on the elements that are produced, because some of them are opaque to different colors of light. If you have certain elements called the rare earth elements, they're opaque to blue light, and so you get a red glow. If you don't have enough of those elements, then the elements that remain are not opaque to blue light, and so the glow is blue. And both things can happen at the same time. So like if one part of the material produces lots of the rare earth elements, then you'll get red from that part. And if one part of the material produces none of those, then you'll get blue in that part. And this is actually what we saw. So this is a picture from August 17, 2017, when the detection of the neutron star merger was made. This is two pictures side by side, I should say, and it's a composite image. The blob in the center is a galaxy, and the blue dot at the top left in the left panel, that is the afterglow, the blue afterglow from the merger, from the radioactive decay of all the heavy elements that were produced in this event. 4 days later, you see that dot has turned orange. That's the red glow from the radioactive decay of heavy elements that were produced in this event. And this observation, the light, is called a kilonova. Now, I'm going to focus just on one piece of this problem for the purposes of this discussion, which is that disk of material falling onto the remnant. But all parts of this problem are quite interesting. And it turns out that for the purposes of nucleosynthesis, it turns out neutrinos play a crucial role. And the reason for that is that neutrinos, we talked about how they, in say beta decay, you convert a neutron to a proton. Well, that means that neutrinos carry, in some sense, conversion of neutrons and protons. And so when you emit neutrinos of one flavor in one place, you make protons into neutrons. And if you absorb them in another place, you can make neutrons into protons. And that's what this movie is showing. This is a movie from a simulation that I ran in my own research of the disk of material falling onto the black hole. The center thing is a black hole. And the colors here are showing emission and absorption rates of different kinds of neutrinos. So in the red, on the left, red means that electron neutrinos are being emitted. Blue means they're being absorbed. On the right side, orange means that electron antineutrinos are being absorbed, and purple means that electron antineutrinos are being emitted. And what happens in this process is that protons are converted to neutrons in the plane at the equator, so the midplane, and neutrons are converted into protons in what's called the corona, which is a bit vertically above or below this equatorial plane. And this drives up, it drives up the number of neutrons in the center and drives it down in the corona and in the wind, that hourglass shape of material coming out the surface. And this controls the nucleosynthesis, which controls the color that we might see. So I'm going to skip these more technical slides, but this is, for example, a picture of the color that we predicted you might see from such a neutron star merger based on the neutrinos. The neutrinos are absolutely critical to getting these observations correct. The last scenario that I wanted to talk to you about as far as neutrinos in space is supermassive black holes. So here, what I'm showing you is the galaxy Centaurus A, and the gray or brown stuff at the center, that horizontal line, that's the galactic plane. That's the disk of the galaxy. It's a spiral galaxy, much like our own. The blue lines coming out perpendicular to that, that is a jet of material moving very, very close to the speed of light, being blown out by the supermassive black hole at the center of the galaxy. The supermassive black hole is many, many million times the mass of our sun. And as you can see, it has a reach, an influence far beyond the host galaxy in which it lives. This is called, often these things are called blazars or quasars. And the jet of material that they're emitting, it fluctuates sometimes. Sometimes it's stronger, sometimes it's weaker. And neutrinos are produced inside this jet of material. And in 2018, we saw that the jet glows. The glow of the jet brightened for a moment, and that coincided with the detection of a neutrino from the same place in the sky, which was this blazar TXS 0506 plus 056. Really rolls right off the tongue. And the neutrino was detected by IceCube, and extremely high energy photons, light coming from the jet of material, was detected by a space gamma ray detector, Fermi. And they were able to pinpoint that these two detections came very much from the same place in the sky, which is what these graphs are showing. So these plots are showing declination and right ascension are sky coordinates. They're ways you might point a telescope. And then the circles and the dots show the locations in the sky coinciding from the neutrinos and the gamma ray detection. And this really shows that they came from the same place, and that for the first time, we learned that neutrinos are being produced in these jets of material coming out of black holes. So that's some of the exciting things that are currently happening as far as neutrino astrophysics. What's next on the horizon? Well, one thing is gravitational waves. As gravitational wave detectors like LIGO, LISA, et cetera, get more advanced and more powerful, we're going to be able to see further and further away in the universe, and we're going to be able to detect, hopefully at the same time, gravitational waves from, say, a supernova and the neutrinos from the supernova. And then we'll have two ways that we can look deep inside the star as it's exploding and learn more about it. Another place that we might look is the very, very distant past. So this is an image from the Planck telescope of the leftover radiation from the Big Bang. This is called the cosmic microwave background. And it's a bath of photons that were produced, of light that was produced right after the Big Bang. It turns out that there should be an equivalent map of the sky from neutrinos. And we think that maybe the neutrino interactions in this early time might help us explain things like why there's more matter in the universe than antimatter, or what dark matter is. These kinds of deep questions that are huge mysteries right now in science and astrophysics. If we could measure neutrinos from the very early universe, that might shed some light, so to speak, on those questions. And so to stimulate some discussion I'd like to leave you with a couple things that I think are big, interesting, open questions as far as neutrino science. One is, how do neutrino oscillations fit into the standard model of particle physics? Another is, what is the mass of the neutrino? We know that neutrinos are massive particles, not massless like photons, but massive like electrons, but that the mass is extremely tiny, far too small for us to have measured so far. As I mentioned, we might wonder, can neutrinos help us explain it and why there's mostly matter in the universe, not antimatter? We know that there were, in the very early universe, there were a lot of neutrinos. How does that fit into the structure of our universe today? How did neutrino oscillations change our understanding of supernovae and neutron star mergers? I didn't really talk about this, but we talked that neutrinos can convert from one type to another. If they do, then you might emit a neutrino that powers, say, a neutron, the decay of a neutron into a proton and an electron. But by the time it gets absorbed somewhere else, it might be a muon neutrino. And it doesn't do that anymore. It powers a different kind of nuclear reaction. And if that's the case, that's going to dramatically change the nucleosynthesis in, for example, neutron star mergers. So how does that fit into our understanding of neutron star mergers? And some people have suggested that there might be another kind of neutrino, the stereoneutrino, which is a candidate dark matter particle. So at that point, I'm going to stop and let's have a discussion, and hopefully you have some good questions. I'll turn on my camera again now.
I wanted to thank you, Jonah, for that really interesting presentation. And I'm sure we'll have lots of questions. So here comes the first question. What is the process by which scientists figure out how to invent the colliders? I guess I'm not sure what they mean by the colliders.
Yeah, so perhaps they're referring to like particle colliders, like CERN. Mm-hmm. Yeah, I'm not an expert on this because particle colliders are developing and running particle colliders is a whole huge field of physics, but I'll do the best I can. Often the way that this starts is a question about what kind of physics questions can you answer if you could smash two particles together at a certain speed, right? And why would you want to smash two particles together at a specific speed? The reason is that when particles collide, they can convert the kinetic energy, the motion of the speed, into you can generate particles actually out of nothing. So it turns out you can convert energy into matter. The velocity of the collision can be converted into different kinds of particles, which you might not otherwise be able to see. So one example of this is you can produce neutrinos in these kinds of collisions. And so you might look for that. Another example is the Large Hadron Collider, which was used to famously detect the Higgs boson. We knew that the Higgs boson we thought it had a certain range of potential mass, but we hadn't been able to produce it. Well, the way we were able to do it was essentially by using Einstein's E = mc squared and firing particles at each other with enough energy that mc squared allowed us to generate the Higgs boson. So that's one reason that's one way that people sort of decide how to design and build different particle colliders. Hopefully that answered your question. If not, send another one to Joyce.
Okay, thank you. Okay, our next question is, what is the energy distribution of cosmic neutrinos?
Oh, great question. So it really ranges over the entire, basically from any energy above approximately 1 mega electron volt. An electron volt is a unit of energy where the idea is that it's the amount of energy required to move an electron, a single electron, over a potential barrier of 1 volt. So that you can think of this in terms of electronics, right? So you have an electron and you put a volt on it and you try to move it. So that's a lot of energy for a subatomic particle. And a mega is a million, right? So, no, it's a billion. So it's a lot, is the point. And then basically, the higher the energy of the neutrino, the further away it came from. So 1 MeV neutrinos might be produced, for example, in a galactic supernova. but the neutrino that was detected by IceCube from the Blazar was something like 100 MeVs. And as you might expect, the higher the energy they are and the further away they come from, the fewer of them we see. So there's a cosmic neutrino spectrum, so to speak, that looks like it's a power law. So it decays as 1 over energy to the, I don't remember the power. It might be 2 or 3, I think. Actually, it swaps at some point and the power becomes steeper, but it's a decay. It decays.
So Steve Becker has a comment that it has also been postulated that the neutrino is its own antiparticle.
Yes.
Another thing you could put on your big open questions.
Yep, that's true.
Okay, Marilyn asks, what fraction of cosmic energy is in neutrinos? There's another hard question.
That's a really hard question, especially because it changes with time. So there was a point in the distant past when it was something like 90% of the energy of the universe was in neutrinos. Today, it's a lot less. If neutrinos are dark matter, then it's something like 25%. If the dark matter particle is not a neutrino, then it's something like 1%. It's a fraction of the amount of baryonic matter in the universe. And what's going on there is that over time, matter has become less and less hot and dense. In the very early universe, everything was super hot and super dense. And there was a point where atoms and nuclei couldn't form. And at that point in the universe's history, pretty much everything was either a subatomic particle, like a quark or something, or a sub-neutron or sub-proton particle, like a quark, or a gluon, or a neutrino. But over time, things expanded and cooled, and material like us atoms and neutrons and protons was able to form, and neutrinos became a less and less substantive part of the energy content of the universe.
Okay, thank you. We have a question about what accounts for the asymmetry of particle emission above and below the supermassive black hole that you showed. You might have to go back to the picture.
I think, do you mean this picture? I think that asymmetry is introduced by the artist. Typically, the jets from a supermassive black hole are pretty symmetric.
So this is an artist's picture of what it would look like.
Yeah. Okay. This is because it's an artist's picture, not the real thing.
Mm-hmm. Okay, another question from a non-physicist regarding the neutrino mass. Neutrino detection seems to involve detecting and measuring the output of a neutrino collisions. Isn't this enough information to determine the neutrino mass?
Yeah, that's another really great question. Yeah. So the answer is no. And again, it comes from the fact that there's this E equals MC squared thing, right? So when a neutrino bounces off of something else, what you can detect is the mass of the neutrino plus the amount of energy it was carrying due to its motion. But you can't just detect the mass. And most neutrinos are traveling so fast and their mass is so small that the mass is just dwarfed by the amount of energy, the amount of kinetic energy it has.
So please type more questions in because we don't have any more in the queue right now. But while we're waiting, I have a couple of questions. One of them I tried to ask while I was muted at the beginning. It was about the IceCube experiment and how that experiment was built. You have this big block of ice that was, I guess, there before. And did they drill holes straight down deep into that ice to put those detectors in? And does it matter if that ice isn't uniform to the detection?
Oh, that's really tough. I can answer a part of that. I don't know about the other part. So yeah, they basically took like the same kind of drills that you use to produce ice cores, you know, that pull out like a big giant column of ice from the Antarctic ice sheet, and they use those to drill in to make these tubes where they could put the detectors. I do not know how they deal with the fact that the ice is not uniform. I guess probably just very, very careful calibration, but I'm not sure about that part.
I'm not even sure how you calibrate a neutrino detector when you can't, they're so hard to detect. You can't just make neutrinos on Earth, I think, and send them through there, right?
Yeah,
Maybe
well, you kind of can, because we have the detector is intended to detect like extragalactic neutrinos, right? So maybe you could use, and I'm guessing here, maybe you could use like solar neutrinos or atmospheric neutrinos to calibrate the detector.
Or maybe I know at places like Fermilab, they would do accelerator experiments and they would make neutrinos and then you could send them towards a detector, but I don't think that's done with this one.
Yeah.
I don't know. Okay. Well, I don't, this is probably not your area, but it was just interesting to think about how would you measure something that's so hard to measure. So
yeah, well, that's a really good question. I don't know the answer.
Okay, so we have a new question. If the sterile neutrino exists and is the dark matter particle, would it behave the same as other neutrinos?
Great question. No, it wouldn't. The sterile neutrino, to be sterile, it would have to not oscillate into the other forms of neutrinos somehow, right? Because otherwise we would have been able to tell that the total amount of neutrinos being produced is not right. And it would also have to be produced in a different set of neutrino matter interactions than the ones we have good understanding of. So that's why it's called sterile, is because it interacts less. It interacts less with the other neutrinos and less with other kinds of material.
Okay. Please type more questions in. We have more time. Rick has a trivia question. What sci-fi disaster movie gave rise to the quote, "The neutrinos are mutating," which caused the destruction of the Earth?
Oh, was that the core? I think that was the core. Rick can tell us whether or not I'm right.
Okay, I'd have to unmute Rick to tell us, but unless he writes something in the chat. All right, here it says the movie 2012 was released in 2009. If the name of the movie is 2012, the premise was that neutrinos from the sun mutated into something that melted the Earth's core, causing the crust to violently move around. Oh, great.
Interesting.
It sounds like the name of the core would be a good name for the movie instead of 2012. So obviously it didn't happen. Yeah, that's not going to happen, I don't think.
No, the neutrinos cannot do that to the. They can't mutate, whatever that means, and they also can't disturb the core of the Earth in that way.
Okay, we have another question. What is the cause of higher than expected neutrinos from the sun? Extragalactic neutrinos, and then I think she says higher energy, that is. Cause of higher than expected neutrinos from the sun.
Not quite. Yeah, I'm not quite sure I understand the question. The neutrinos, now that we have found them all, because we've learned about neutrino oscillations, with neutrino oscillations included, the number of neutrinos and their energy coming from the sun is pretty well understood at this point. There aren't higher than expected energy neutrinos from the sun. There are lots of high energy galactic and extragalactic neutrinos. That's coming from things like that blazar or from supernovae.
Okay, Rick has another addendum to his message. The neutrino phrase about the neutrinos are mutating was voted the silliest line in any movie as of 2018. But they really do mutate. They turn into muon and tau neutrinos.
That's
So,
true.
yeah, so it's not necessarily that silly.
That's true.
Okay, well, I'm waiting for more questions. I have another question of my own about the cosmic microwave background, and you said that the future we might be able to detect neutrinos from the Big Bang. What would that look like? Is that possible? Do we need detectors to do such a thing, or is it in the near future?
It's not in the near future. That's very speculative on my part. Hopeful, I guess. I think it would look a lot like, ice cube kinds of detectors, where you basically make a really humongous surface area or volume through which the neutrinos might pass so that you can catch them. And the tricky part about the cosmic neutrino background is actually that those neutrinos are super low energy, not super high energy, because just like the cosmic microwave background is low energy photons, the neutrinos have also lost a lot of energy since the Big Bang. So it's a very challenging detection. I don't really know how it would be done, but if we could do it, it would be really, really interesting.
Yeah, I think it would answer a lot of questions. Okay, we have another question. Were flavored neutrinos predicted? I.e., did theory predict neutrinos needed flavors, or were flavors observed and then the theory adjusted to accommodate them? Seems this relates to existence of sterile flavor neutrinos.
Yeah, great. Yeah, so neutrino flavors were predicted first, and also observed. Wait, it's both, because when we saw neutrino interactions, that's how we decided on the flavor. So it's no coincidence that in beta decay, you emit an electron and an electron antineutrino. Let me go back. That's because it turns out that there's a special conserved quantity called lepton number that needs to be carried. So the neutron to proton conversion and spitting out an electron, if you lose the electron, then and make a proton, then it turns out that this lepton number is not conserved. You've created an electron from nothing, and so you've increased lepton number. That's not allowed. Electron antineutrinos carry negative lepton number. They carry negative electron number, so to speak. And so they make the conservation law hold. So this is like you can't create or destroy mass and energy. It's a similar idea, but for this other special subatomic quantity called lepton number. And so that's where the flavors come from. They come from the kinds of reactions that they are required to participate in. So electron neutrinos are in reactions where electron-lepton number is required, muons for muon number, tau neutrinos for tauon number. So they're about the conservation of these special fundamental particles. The neutrinos can carry around, they can kind of cheat the conservation law because they carry around the equivalent conserved quantity. So that we knew about that from the beginning once we understood what was going on in beta decay. Enrico Fermi, I think, could be wrong about that, made this prediction about beta decay. And he called them neutrinos as like, I think it's something like little neutrons. But don't quote me on that. I could be wrong about that entire historical fact. But the fact that the flavors were required was sort of known from the beginning. On the other hand, like we talked about, the oscillations were totally unexpected. that was an experimental observation that then required us to go back to our understanding of flavors and revisit it.
Okay, so we have a question which I hope you'll like. What is your favorite thing about neutrinos?
What is my favorite thing about neutrinos? Yeah, that's hard because there's so many cool things about neutrinos. I guess I'd say my favorite thing is this X-ray machine thing, right? The fact that you can see, if you look at neutrinos from, say, an exploding star, you can see inside the star. I think that's really, really cool. Maybe just because it makes me feel like, stars aren't so different from us, right? They need to be X-rayed too.
All right, another question. What percent of neutrinos are detected through a given detector? Wikipedia indicates that's a very small number.
It's really super small. It depends on the size of. It depends on the size of the. Does it depend on the size of the detector? It does, but so roughly, here's what you should think about: is that the size of a neutrino, so to speak, if you were to try and create a net to stop neutrinos, the size, quote unquote, is roughly 1 part in 10 to the 26 centimeters. This is what's called the neutrino cross section. It's not really a physical size, but it's sort of the distance away from a neutrino that you have to be to catch it. And so that's why you need giant detectors, is because imagine building a web and you're trying to catch neutrinos in your web. They're going to go right through your web, but some of them are going to hit the filaments of your web. And the bigger web you have for the same size filaments, the more neutrinos you're going to catch. So for a given detector surface area of 10 to the say, if you have a detector with a surface area of 1 centimeter, you're only going to catch 1 neutrino in every 10 to the 26. So the fraction is absolutely tiny.
There's a comment that someone looked on the wiki for IceCube, and it says they used a hot water drill to make those holes. So that'll be interesting to read up on the technology of how they made IceCube, I think.
Yeah, that's really cool.
Fun to look at that. Yeah. So here's another one. Back to the predictions. Does this conservation principle also predict the sterile neutrino? And if so, how does this relate to attempts to understand dark matter? I guess this is the conservation of lepton number you were talking about.
Right. Yeah. So the conservation of lepton number. Let me invert that question. If the sterile neutrino exists, what kind of subatomic particle what number does it conserve? We don't know of one, but if it turns out that the sterile neutrino is, in fact, the dark matter particle, then that implies another conservation law that we didn't know about, which would be very, very exciting.
Okay, another question. Is the source of galactic neutrinos expected to be isotropic?
Ooh, that's good. No, kind of. The source of extragalactic neutrinos is expected to be approximately isotropic. The source of galactic neutrinos is actually quite anisotropic. It is mostly focused on the galactic core. And that's because that's the place where stars are oldest. And so that's the place where you might expect the most sort of galactic supernovae, although we haven't seen one since 1987A. And that's also the place where our own supermassive black hole lives. And that is producing neutrinos. So galactically, it's quite anisotropic.
Thank you, Jonah. Thank you so much for sharing all of this information and knowledge with us tonight. So thank you all again for tuning in. And thanks again, Jonah.